All right, let's continue talking about fluids. Last time we discussed density, and the equation for density was mass divided by volume. Pressure, we found, was the force applied to an object over the area over which the force is applied. We had Bernoulli's equation, which said P1 plus rho G H1 plus 1/2 rho V1 squared is the same as P2 plus rho G H2 plus 1/2 rho V2 squared. And this equation, Bernoulli's equation, we use a lot for things like pipe systems, fluids flowing through pipes. The pipes can constrict or expand. They can move up in height, down in height, and so forth. And this gives us a relationship between the pressures at different points in the pipes. And then we had the continuity equation, which said A1 times V1, that's the area, the cross-sectional area of a pipe, times the velocity of the fluid flowing through that part of the pipe, is the same as the area of a second part of that same pipe times the velocity flowing through that part of the pipe. And this equation, of course, relates how big a pipe is to the velocity flowing through the pipe. And it says basically, if you constrict a pipe, the fluid will flow faster, and if you expand a pipe, the fluid will flow slower. And basically, this continuity equation tells you about the flow rate. So something like 5 gallons of water flows per second. That's what the flow rate is. Well, there's another equation we'd like to know, and this equation relates the pressure in a fluid to the depth inside the fluid we're measuring. So we know, for instance, the reason we haven't explored the oceans too well is because as you go deeper and deeper underwater, the pressures get higher and higher, and our bodies, of course, can't take those high pressures. And even submarines and things that we build can only withstand a certain amount of pressure. So the equation that tells you how much pressure there is at a certain point in a fluid, a certain depth, is given by rho G H. So H, of course, being the depth or the height. Of course, we usually think of it as depth because we're thinking of going down in height rather than up in height. And so that's the equation. Let's say we have an example of a diver dives 100 meters underwater. How much pressure will he feel? Well, to properly discuss things like this, there's one more thing we have to discuss about pressure, and that is absolute pressure versus gauge pressure. And so what this deals with is basically the fact that on Earth, the atmosphere we live in causes a pressure on us. So everywhere on Earth, there's some amount of pressure, 1 atmosphere of pressure, on all objects. And so there's some pre-existing pressure on everything, and then we can increase or decrease that pressure by manipulating. So for instance, we say there's a certain amount of pressure when a diver goes down 100 meters. Well, what we mean is, okay, here's the water. Let's say the diver's down here. He goes down a certain height, h. And we want to know what's the pressure on that diver. Well, it turns out, before he even gets into fluid, the pressure at the surface is already atmospheric pressure. So the pressure down here is going to be whatever the atmospheric pressure is plus this rho GH term. And so the difference between caring about the fact that atmospheric pressure was already there and only worrying about the change is absolute versus gauge pressure. Absolute pressure is the total pressure, which means it's atmospheric. So the normal pressure everything feels just because it exists in this atmosphere, plus the gauge pressure, where the gauge pressure is the change due to going down in depth or whatever we're talking about. So you have to be very careful when you work on problems to understand which of these two, the absolute pressure versus the gauge pressure, the question wants you to give. And most of the time the problem will say, hey, calculate the absolute pressure, or it may say, what pressure would a gauge read if you go down a certain amount of meters or whatever. So that's the difference between absolute and gauge pressure. Gauge pressure is just pretending like we're at zero pressure. Now I'm going to go down in depth. How much more pressure do I get? Absolute pressure is the total amount of pressure, which includes gauge pressure, but also the fact that I was already under pressure because of the atmosphere. So, what I'd like to do now is a couple of examples on some of this stuff, so we can get used to the type of questions we may get on a test or homework or things like this. So let's take the first example. Let's say a diver is diving in a freshwater lake to a depth of 20 meters. What is the absolute pressure acting on the diver? Okay. So, first thing we know is when we want to find absolute pressure, what we need is atmospheric pressure. So that's just the pressure you feel because you live on Earth, plus the gauge pressure, which is the difference in pressure from atmospheric to whatever it is you're doing. Well, the first thing to note is that atmospheric pressure is a constant. I mean, relatively speaking, we're going to assume we're at sea level and all of that. It turns out atmospheric pressure is 1.01 times 10 to the 5th pascals. It's always going to be that for the problems we're going to work on. Obviously, if we're in Denver and we're a mile up, the pressure in Denver is different than the pressure in New Orleans, which is below sea level, and so forth. But we're just going to use this as a constant number for atmospheric pressure. So gauge pressure then, well, to calculate this, the equation we're going to use is the equation for the pressure-depth relationship, because the reason we're changing pressure is the fact that we're going down a certain depth in water. So this pressure is going to be rho times G times H. Well, rho, that's the density of the fluid that our diver is going to be going down in. We're told this is freshwater lake, so it's just the density of water. Density of water is 1,000 kilograms per meters cubed. G, of course, that's just 9.8 meters per second squared. And the depth, the height, or the depth in this case, is going to be 20 meters. So our equation for the absolute pressure acting on the diver is going to be 1.01 times 10 to the 5th plus 1,000 times 9.8 times 20. And when you calculate this out, you get 1.98 times 10 to the 10. I'm sorry, I calculated that wrong. It's actually 2.97 times 10 to the 5th pascals. So here, a fairly clear example. Something's going down a certain depth in a fluid. We want to figure out the pressure on that thing. In this case, we want the absolute pressure. So, because we want absolute pressure, that means we need to take into account atmospheric pressure, which is a constant. And then we need to calculate the change, and in this case, the change is occurring because of the depth in a fluid. And we plug the numbers in and we get our answer. All right, another example. Let's say we have a pipe. That pipe then constricts and keeps on flowing. Let us say the radius, R1, of the beginning of the pipe is 50 centimeters. And the radius R2, that is the radius of the constricted part of the pipe, is 10 centimeters. If the fluid flowing through the first part of the pipe flows at a speed of 20 meters per second, the question is going to be calculate the difference in pressure from points 1 and 2. So point 1 in the pipe, of course, that's the left side. That's where the pipe is larger. Pipe then constricts down, and we have the other end of the pipe, point 2. And we want to know the difference in the pressure between these two points. Well, the equation we want to use for this is Bernoulli. So Bernoulli says P1 plus rho GH1 plus 1/2 rho V1 squared is P2 plus rho GH2 plus 1/2 rho V2 squared. Now, some things to mention. Let's assume, usually the problem would tell you this, but assume this is water, so the density of water is just going to be 1,000. Also, note that our pipe does not change heights. It stays at a constant height. The only thing that's changing is the size of the pipe. So rho GH1 and rho GH2 are the same, so they cancel out. We don't care about those terms. So we're left with the equation P1 plus 1/2 rho V1 squared is P2 plus 1/2 rho V2 squared. Now P1 and P2, those are the pressures at either end. Rho, that's the density of the fluid, that's my 1,000. V1 and V2, that's the velocity of the fluid at either end of the pipe. So if I want to solve this problem, what I need to do is have P2 minus P1. I want the difference in pressures. So I'm going to bring P1 over to the right side, and I'm going to bring this term over to the left side. And what that leaves me with is P2 minus P1 on the right equals 1/2 rho V1 squared plus 1/2 rho, minus 1/2 rho V2 squared. So P2 minus P1, that's what I want to calculate. That's the difference in pressure. So all I need is to plug in the numbers on the right side. The problem is I don't know what V2 is. I don't know the velocity in the second part of this pipe. I know the velocity of the fluid on the left, that's 20, but V2 I don't know. So I need to calculate it. Well, to calculate it, this is the continuity equation. It relates the velocity of the fluid to the size of the pipe. So I'm going to say A1 V1 equals A2 V2. All right, so for the one side, the left side, A, cross-sectional area, that's pi times R1 squared. That's A1. Times V1, that's my 20. Equals A2, that's pi times R2 squared times V2. And so I want to solve this for V2. So I get V2 is pi times R1. R1 is 50 centimeters. But I don't want centimeters, I need meters, so it's going to be 0.5 squared divided by pi times R2. And R2 is 10 centimeters, so that's 0.1 squared times V1, which was 20. Notice here the pi's happen to cancel out, and if you calculate this out, you get 0.5 squared over 0.1 squared times 20 gives you 500 meters per second. So now I know my V2, I can plug it into my equation over here, and what do I get? 1/2 times 1,000 times 20 squared minus 1/2 times 1,000 times 500 squared. And when you calculate this out, you get minus 1.25 times 10 to the 8th pascals. So there's a difference in pressures between the left side and the right side of this pipe, purely because of the constriction. Notice what this says. I get a negative pressure difference. That means the pressure on the right is smaller than the pressure on the left. And that makes sense, as I said before. When a fluid flows faster, the pressure drops. That was our discussion about flight and how Bernoulli's equation can explain why airplanes can take off, because the fluid, the air, flowing over the top of the wing flows faster than under the wing. And so the pressure on top of the wing is less than the pressure below the wing. So you have more force under the wing pushing up than you do on top. And that's exactly what we see here. The smaller pipe has a faster fluid. Faster fluid means less pressure, and that's why the difference in pressure here turns out to be negative. So I hope these examples made some sense, and we will continue next time.